This next module in Gen Chem Lab, we're going to be talking about acid-base reactions. In particular, we're going to be talking about the Lewis acid-base model. In the Lewis definitions of acids and bases, an acid is any substance that can accept a pair of non-bonding electrons, and a base is any substance that can donate a pair of non-bonding electrons. So if you look at our examples here, we know that BF3 is the most stable version for boron. It's one of the Lewis structure exceptions, right? Because it doesn't like to have 8 electrons around it, rather 6, but its formal charge then is 0. That being said, it has a trigonal planar shape and it has an extra empty p orbital on it. And so that boron has an open space to accept a pair of non-bonding electrons to make a new bond. SO3 also, right? Sulfur has 8 electrons, but it can expand its shell, right, to accept more electrons there and create a new bond in that empty space. The base then is anything that looks like has a lone pair to donate. These are typically non-bonding electrons that will donate. So hydroxide is a great example because it has actually, the oxygen has 3 lone pairs of electrons that it could donate. Any halogen ion, right, has non-bonding pairs of electrons that it could donate. And nitrogen is a super good Lewis base because it has that extra pair of non-bonding electrons that it would like to donate to a reaction. So this Lewis acid-base reaction is consistent with the oxidation reduction model, but instead of a transfer of electrons from one species to the next, the 2 species come together to share electrons. So there's no change in the oxidation numbers here, but it's still about electrons, which is a little bit different than that Bronsted-Lowry definition where we're talking about the proton, the H+, that would go from one molecule to another. Here we're still talking about electrons and where electrons are. And when you move on to organic chemistry, this is going to be, 80% of the reactions that you'll see will be related to where the electrons are and how you move electrons from one place to another. So here we have a Lewis base, O2-, right, going to attack your Lewis acid or that empty space. And now you're going to form an adduct. So again, they're not transferring electrons from one place to another, but you're donating electrons and you are accepting electrons to create a new species that is usually an adduct or a new, where they combine to share a new bond. So here's your Lewis acid, your boron with that extra empty p orbital. That's going to bond with the extra lone pair on fluorine and create your BF4. Okay, now you'll see that a lot of times you'll end up with a complex ion, but that is okay. The base, the Lewis base that has the extra lone pair, is called nucleophile or nucleophilic, which means it's nucleus seeking. So it's looking for a positive charge that it can share its electrons with. And the Lewis acid is called an electrophile or an electrophilic species, and it's electron seeking, right? So it's looking for a lone pair of electrons to bond with. And again, you usually end up with this adduct, right, where you've created a new bond. So you haven't transferred electrons from one place to another, but now you're sharing electrons. So in the last module that we did with crystal violet and hydroxide, hydroxide was actually that Lewis base. The nucleophile that's looking for a positive charge or some place to put one of its extra pairs of electrons. So it's going to share with crystal violet this carbon that's in the center. And now electrons get pushed so that you have this, these 2 electrons in the double bond that are being shared here are now going to be shared between these 2 carbons. And that's going to push these electrons that are shared here to these 2 carbons, right? Just the pi electrons that are being shared, not the sigma bonds. Okay, and that's going to push these electrons into a lone pair on the nitrogen. And now my nitrogen is just like these other 2 nitrogens, which have a formal charge of 0 rather than a formal charge of plus. So that's a more stable situation. And now that lone pair is taking up that last sp3. So this was sp2. We moved some electrons so that it's sp3. And now that carbon it has a full sp3 shell where it's sharing electrons now with that hydroxide. So what that did was that broke the sp2 network. So now we have sp2 network here, we have an sp2 network here, we have an sp2 network here, and they used to all be connected through the sp2 in the center, but now we have an sp3 in the center. So to put this together with our SAMs, if you think about the SAM molecule itself, the SAM molecule has that amine on the end, and it is a really great nucleophile, right? So the nitrogen has a lone pair of electrons that it can donate to create a new adduct that will behave just like hydroxide did and attack that central carbon. All the electron will shift and put that lone pair on nitrogen. So now we have a formal charge of 0 on that nitrogen, and now we've created a new adduct with crystal violet, which is now colorless, and our SAMs molecule. So looking forward to this module, we're going to show you how the SAM molecule does work as that base. It works the same way that the hydroxide does with the crystal violet. But the challenge for you all will be to figure out how to make this work when this SAM molecule is attached to a surface. You'll have to think about concentration considerations and play around with it a little bit. So this module will be talking about acid-base reactions. We'll also be talking about concentration and equilibria effects, but it's going to be a little more open as far as to what you want to investigate.